Welcome to class 86. Why is this a special day? Tell me why. It's not a special day because it's class 86. Why is it special? Guys, this video you're watching right now is the last time that you are going to learn physics from Mr. Randy. I'm not joking. Why? Because next class, Thursday, I've decided to make a exam review, because that's our last actual physics class. I decided to make it blue. The video is blue today. You have no idea, I'm serious, you have no idea how long it took me to make this video blue. I'm not even going to tell you how long it took because it was a little bit frustrating. But I made it blue for you, so listen carefully to everything I say today. Okay? Here we go, class 86. This is a theory day, okay? So we're going to talk about I cannot believe it. This is the last time that I get to teach you physics. It came so soon. It came so fast. But, I mean, life goes on, and let's learn, okay? Let's learn right now. Guys, today is a theory day, as I told you, and I'm going to teach you the basics of the theory behind subatomic physics, okay? I decided to leapfrog atomic physics. We haven't done much with atomic physics this year, but I really wanted to spend a little bit of time with you guys in subatomic physics. So that's what we're going to learn today. You can see where there's kind of 9 different discussion topics we're going to have, okay? And this is really sweet stuff. It's really interesting. So you better listen, because if you don't listen now, you're never going to have another chance to listen to me teaching you something. Okay, so here we go. Most of the stuff I tell you today, I think, is going to be information that you have never learned. Okay, and a little bit of it, like number 1, is information you probably knew. Okay, so let's do this. We're going to be studying the nature of atoms. Okay, today. And so, what are atoms made of? They're made of 3 components. That is, electrons, protons, and neutrons. Okay. Now, I want you to think about, like, if we say, like, boys and girls, what's another way to say boys and girls, but just in one word? Kids or children, right? Boys and girls in one word would be children. What is one word to say protons and neutrons? Nucleons. It's the components of a nucleus of an atom, okay? Remember, electrons are not part of the nucleus of an atom. Only protons and neutrons are in the nucleus, okay? Most atoms contain protons and neutrons. An exception to that would be hydrogen. Hydrogen just contains 1 proton, okay? There is no neutron inside the nucleus of a hydrogen atom, okay? Hydrogen is also the lightest element. I just want to confirm that. Is there a neutron in a hydrogen atom? A normal hydrogen atom does not have any neutrons, okay, inside its tiny nucleus. I told you, don't forget that. Also, what is the lightest element? I was right 2 times in a row. Okay, so typically the nucleus of an atom will have neutrons and protons, okay? And neutrons and protons combined, like I said, are what we call nucleons, okay? Now, what in the heck is that, a femtometer? Well, you guys recently have learned what is a picometer, right? 1 times 10 to the negative 12 meters is a picometer. How much is a picometer? How many meters is a picometer? Watch. Google heard me say watch. How many meters is a picometer? Are they joking us right now? One picometer is how many meters? 1, 2, it's going to be 12 zeros, I'm telling you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a 1 with 12 zeros is a trillion, okay? Because a 1 with 3 zeros is 1,000. A 1 with 6 zeros is a million. A 1 with 9 zeros is a billion. A 1 with 12 zeros is a trillion. And a 1 with 15 zeros is a quadrillion. Okay? So 1 quadrillionth, right? 1 quadrillionth of a meter is a femtometer. Okay, why is that significant? It's because we use the femtometer to measure subatomic distances and measurements, because that's the most practical unit to use because they're so tiny. The nucleus of an atom is unimaginably small. If you think you know how small it is, you don't know, because it's that small. Okay, and we have to use what we call femtometers to measure subatomic distances. Okay, now what is a mass number, atomic number, and neutron number? Okay, now let me say this: the atomic number is the number of protons. Okay, the number of protons is the atomic number. Boom. And then the neutron number is the number of neutrons. So atomic number corresponds to protons. Neutron number corresponds to neutrons. Mass number is the number of protons plus the number of neutrons. Okay? I don't know who decided to make the mass number correspond to the variable A, and then the atomic number, which is protons, correspond to Z, because you would think that atomic number would correspond to A, but it's not. Mass number is A, atomic number is Z, neutron number is N, okay? So once again, N is number of neutrons in the nucleus of an atom, Z is number of protons in the nucleus of an atom, and A is the sum of the protons and neutrons. If you add the protons and neutrons, then you get the mass number. For example, the most common isotope of carbon on Earth is what you call carbon-12. Okay, carbon-12 has a mass number of 12. Okay, that's why it's called carbon-12. It has a mass number of 12. So the A for carbon-12 is 12. Okay, now interestingly, carbon-12 has 6 protons and 6 neutrons. It's not always they're not always the same number in all atoms, but in the case of carbon-12, there is the same number of protons and neutrons. They're both 6. So the 6 plus 6 will give us the 12 of carbon-12. Okay, so now I want you to think about something. Okay, here we have some potato chips. You can see that this video is mirror image, right? I look more beautiful if I mirror it, so I always make it mirrored. Just kidding. It's just if I don't have it mirrored, then I move this way, and then the video moves that way, and it's like really annoying. Okay, so here's some potato chips. Why is this significant? I want you guys to imagine Luis Fernando. Okay, hey Luis, come up here. All right, cool. Here's Gringo Luis. Hey guys, my name is Luis. Now I want you guys to imagine Luis Fernando right here. And trust me, I thought about this before the video, and I was like, should I say his name because we're on the internet? And I said, you know what? It's the last class. It's class 86. I'm going to say his name, even though this is going to be on YouTube forever. Congratulations, Luis Fernando. You're on the internet forever. Now, here's Gringo Luis Fernando, also known as Mr. Andy. Okay, and I want you to imagine that Luis Fernando turned into a potato chip. Okay, what do I mean by that? What I mean is that if you take out all the water of Luis Fernando and you just have a potato chip version of Luis Fernando, basically you have Luis Fernando but with no water. My question is, if we had a potato chip version of Luis Fernando, how much of that potato chip of Luis Fernando's body is carbon? Okay, so let's say we took all the water out of Luis Fernando, and then we put him on a scale and we said, okay, how many kilograms is all of the dry mass of Luis Fernando? Well, how much of that is carbon? About half of your dry mass, half of Luis Fernando's dry mass is carbon. It's carbon, okay? And 98.9% of the carbon on Earth is carbon-12, okay? Carbon-12 right there. And carbon-12 happens to be the most abundant form of carbon by far in your body, okay? So once again, remember, like coal power plants are mostly use carbon, okay? Also, diamonds are made of carbon. What element are diamonds made of? Okay, carbon. What is graphite made of? Okay, graphite is the material in your pencil that you write with. Graphite is made of carbon. 50% of your dry mass is made of carbon. Now listen to this. What is the most basic element of life? There's another question I asked it before they gave me carbon. The idea is that like your body has a ton of carbon in it, okay? And yeah, so 50% of your dry mass is carbon. Now think about this. Carbon-12, that is the carbon that has 12 neutrons and 6 neutrons and 6 protons is not the only kind of carbon on Earth. Okay, now let me say something else about nuclei before I tell you about other types of carbon. The number of protons in an element does not change. Okay, hydrogen always has 1 proton. Carbon always has 6 protons. But what does change? There's something that does change, and that is the number of neutrons. Okay, carbon-12 has 6 neutrons and 6 protons. Okay, carbon-13 has 7 neutrons, but like I said, number of protons don't change. So carbon-13 still has 6 protons. What about carbon-14? Carbon-14, also known as radiocarbon, is an isotope. Okay, when the number of neutrons changes, we call those different isotopes of an element. So we can say the carbon-12 isotope, the carbon-13 isotope, and then carbon-14 isotope is actually a very useful isotope. Okay, it's radiocarbon. That's what we call it. Why is it useful? Well, radiocarbon is before I tell you about radiocarbon, let me tell you a little bit more about carbon-12. Carbon-12 is okay. So about 98.9% of the carbon on Earth is carbon-12. Okay, and then about 1% of the other carbon on Earth is other isotopes. How much percent of carbon is carbon-12 on Earth? About 99. I said 98.9. Okay, it's carbon-12. So 99% of the carbon on Earth, our textbook says 98.9% carbon-12. Okay, some of it is carbon-13, and then some of it, a very small amount, is carbon-14. Okay, radiocarbon. Why is that important? Okay, carbon-14, radiocarbon, is unstable. Okay, so it decays, is what I'm saying. It decays into what? Well, it decays into what we call nitrogen-14. Nitrogen-14. The nitrogen-14 is a little bit irrelevant. We're not going to talk much about that. But what do we use carbon-14 for? Carbon dating. Carbon dating. Okay. If you have studied paleontology, what do you call the study of dinosaurs? Yeah, paleontology. And they tell you, oh, this dinosaur died this many million years ago. This dinosaur died this many million years ago. How do they calculate that many millions of years? I'm going to close my potato chips so I can eat these after. Else they're going to get all stale if I don't close it. Boom. Okay. They determine the age. They determine the age of a dinosaur bone based on how much carbon-14, how much radiocarbon is in a sample of the bone, okay? Because, think about this, carbon-14, first of all, let me say this. Do I believe that that dinosaurs lived millions of years ago? I don't believe that. There's a number of reasons. Number one is if you carbon date an elephant toenail, there's reports that they've carbon dated a live elephant toenail, and it was dated at some number of millions of years. Okay, that doesn't mean that carbon dating is completely unuseful, right? I think it still demonstrates some level of reality. But why do I not believe that dinosaurs lived millions of years ago? Well, number one, there are fossils that have been found. One specifically that I'm referring to of a dinosaur footprint, and then inside the dinosaur footprint is a human footprint with 5 toes. Okay, clearly a human footprint. Okay, what is the only way that one fossil can contain a dinosaur footprint and a human footprint? There's only one way that can happen. That is, basically, the dinosaur was walking. And he stepped in some sort of soft soil, probably like mud. Okay, and then he left a footprint. The dinosaur keeps going, and then what happened? What has to have happened is that the human came, and while that mud or that soil, whatever, the clay or mud was still wet, the human stepped inside the dinosaur footprint. Okay, and then that entire system that contained both footprints was fossilized. Okay, and that's one fossil that's been found. Okay, so in order for there to be those 2 footprints, human and dinosaur, in the same fossil, means that they needed to live at the same time. They needed to coexist. But what does the theory of evolution say? The theory of evolution says that dinosaurs died millions of years. I believe 65 million. They say 65 million years ago. They say that dinosaurs died 65 million years before humans evolved. Okay, so according to how many years ago did the dinosaurs die? Okay, they say that, and many people say it was a meteor that fell to Earth and killed all the dinosaurs somehow. Okay, and then listen to this. When did humans evolve? But fossils of early humans who lived between 6 and 2 million years ago come from Africa. Okay, so we're talking about 60 million years between the death of the dinosaurs and the evolution of humans, according to the theory of evolution. By the way, when you ask Google Assistant a question, you're getting data from the Google search engine. Does Google believe in God? Well, depends on which employee of Google. In general, Google is a how can I tell you? It's a political opponent of Christianity. Why do I say that? Well, I mean, when you look at the Google Assistant answers that it could give, like let's see what happens if we say, "Who is Jesus?" Who is Jesus? Okay, so that's from Wikipedia. Is the quote from Wikipedia? The point is, Google is not necessarily a Christian company. So when they say like an answer to you, they're not necessarily telling you the truth. Okay, evolution is a theory; it's not fact. Okay, and if you tell an evolutionist what I told you about the 2 footprints, I don't think that they would be able to give you a good answer. I've never heard a good answer as to how that's possible. The only way for there to be those 2 footprints together is if they coexisted. And that, yes, it's only one piece of evidence, but there's others. That is one piece of evidence that would help disprove the theory of evolution. Okay, there's verses in the Bible that talk about the Leviathan and the Behemoth, are 2 words that the Bible uses to refer to ginormous animals that many would believe are dinosaurs that people in the Bible witnessed. Okay, alive. And many people would say, it was Noah's flood that actually killed the dinosaurs. Okay, that's why you can find seashells in the Himalayan mountains. I believe, is because Noah's flood, during when the waters rose, the water was even above the Himalayas, and seashells and sea animals were able to be in the area of the Himalayas where Mount Everest is the Himalayas. And that's why you can find fossils of seashells in the Himalayas. Can you find fossils of seashells in the Himalayas? Yeah, even in the Himalayas. Boom. Okay, so try to explain have an evolutionist explain that to you. They would probably give you some explanation, but I believe that was Noah's flood that brought those shells up there. In the same way, probably it was Noah's flood that killed the dinosaurs. Okay, that's a whole other conversation. The point is that that all came from carbon dating. So basically, the more carbon 14 is in a dinosaur bone, the idea is that if there's a lot of carbon 14 in the bone, that means not that much has decayed. Okay, not that much has turned into nitrogen 14. Okay, so if there's a lot of carbon 14, right? Because I told you this decays, it's unstable, and it does not stay carbon 14. It will slowly turn into nitrogen 14 at a predictable rate, at a predictable speed. Okay, so if a bone has a ton of carbon 14 in it, that means the dinosaur did not live super long ago. But if you find a dinosaur bone that has only a tiny bit of carbon 14 in it, that means that most of the carbon 14 has decayed. Okay, has turned into nitrogen 14. And theoretically, that bone came from many, 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 many more years ago. And that's how carbon dating works: is they measure the level of carbon 14 in the bone. But there are flaws in that method, as I just talked about with the elephant toenail, right? Okay, so now we're almost done with this lesson. It's been fun so far. I'm going to miss you guys a lot, so much. But let me tell you a couple more things. Okay, let's talk about the density of a nucleus of an atom. Okay, scientists say that most atoms, I should say most nuclei, have the same density, regardless of how many neutrons and protons are in that nucleus. Most have about the same density. Okay, we've talked about density in topics in the past in physics. Okay, what is the density of water, for example? Well, we all know that 1 cubic meter of water, so 1 meter by 1 meter by 1 meter of water weighs 1,000 kilograms, or 1 times 10 to the 3 kilograms per meters cubed is the density of water. Okay. Now, how dense is? Let me go like this. How dense is a nucleus of an atom? Super dense. Super dense. Because when you look at the volume of an atom, the majority of that volume is empty space, and then in the very middle there's a super quadrillion supers dense little tiny nucleus that contains protons and neutrons. How dense is that? Well, it is if you had a nucleus that was 1 meter by 1 meter by 1 meter, that was pure protons and neutrons, no electrons, no empty space, only the nucleus matter, it would weigh 230 quadrillion kilograms. 230 quadrillion kilograms, because times 10 to the 15 is quadrillion, and then 2 more, 230 quadrillion. Show me 230 quadrillion. Wait, let's go like this. I just want to make sure I'm right about that. Let's go. I want to make sure I didn't tell you wrong right there. 2 point. How many zeros? 230 quadrillion. Fifteen zeros is quadrillion. Yeah, I mean quadrillion is 15 zeros. So 2.3 times 10 to the 17 is 230 quadrillion. Because if we had 2.3 quadrillion, that would be this. let's just say we had 2.3 quadrillion, not 230, but 2.3 quadrillion, this would be a 15, okay, because quadrillion is 15 zeros. But if we have a 17, then we move the decimal 2 places, 230 quadrillion is this number, kilograms for every meter by meter by meter of volume, okay? That's so much, but you can't really grasp. Like when I tell you that's really big, you don't feel like how dense that really is. So let me explain this to you. In my physics class in university in Colorado, when I took this my first year, so I was 18. Yeah, I was 18 or 19 when I took this, so like a year older than you when I took this physics class in university. And guess what I learned in this physics class? I'll tell you. I'm gonna right now put in perspective for you how dense is the nucleus of an atom. Okay, so here we go. First of all, let me tell you, what is a real world example of a super, super, super large nucleus? Well, there's something we call a neutron star. And what that is basically is an entire star that is the result of a supernova. And what is left over after a supernova is one of a number of things could happen. But two possibilities are, number one, a black hole. After a supernova, a black hole could form. If a black hole does not form, then there's a possibility that a neutron star would form. What that is basically a sphere of pure neutrons and electrons with no empty space, just neutrons and protons in a sphere. And that's what you call a neutron star, like a really big sphere. Okay, so now I'm gonna put this density. So the density of a nucleus is also the density of a neutron star, same density, but the neutron star is literally a star, super big. Okay, so I want you to think of a neutron star basically as a big nucleus of an atom. Okay, now how dense is this? It's gonna blow your mind. Okay, it's gonna blow your mind. You ready for this? This is how dense a neutron star is. I want you to imagine I have a paperclip right here. Let me grab a paperclip. Okay. Wait for it. I can't find. Here we go. Okay. Here's a paperclip, right? This paperclip weighs about a gram. Okay, so about 1,000 of these would be 1 kilogram. Okay, now here's what I'm going to do to illustrate how dense a nucleus of an atom is, or a neutron star is. Okay, so here's the paperclip. This is what I learned in my physics class in university. This is the illustration they gave in the textbook. Okay, if you replace, so I want you to imagine that all this metal, we remove the metal, and then instead of this metal, which is, I don't know, aluminum or something, or steel, I want you to imagine we take out the steel, and then we take like a spoon, and we scoop out this much of a neutron star, and then we pour it like into a mold, and then now imagine that we have on Earth a paperclip that is made of neutron star material that is as dense as a nucleus. Okay, because remember, when you look at an object, most of what you're looking at is the empty space between the electrons and the nucleus. Okay, so imagine that this is just neutron star material. Okay, just nucleus material. How much would this weigh? Right now, this weighs a gram, right? Because it's made of metal. But if this was made of neutron star material, how much would this weigh on Earth? How many kilograms do you think? Do you think 100 kilograms? Do you think, so I weigh like, I don't know, 80 kilograms. Do you think it would weigh more than me? Yes, it would. It would weigh more than me. Do you think that this neutron star paperclip would weigh more than a car? Yes, it would. Do you think that this would weigh more than Minerva School? Yes. Okay. This would weigh more than, I have not even told you what I learned in my physics class in university yet, but I'll tell you in a minute. If you take the weight of all like 500 students of Minerva, this neutron star paperclip that's made of nucleus material would still weigh more than all 500 of the students at Minerva. You ready for this? I'll tell you how much this would weigh. This neutron star paperclip on Earth, it's made of neutron star material, would weigh as much as Mount Everest. Mount Everest. That's how dense a nucleus is. It is unimaginably dense. Literally, this volume, but the mass of Mount Everest. I don't even know how many kilograms that is, but that's huge. That is so heavy. Now, what would happen if you dropped this paperclip that was made of neutron star material? Well, it would fall through the Earth. It would fall through the Earth as if the Earth was not there, because the volume to mass ratio is so extreme that this would interact with the Earth as if this would fall through the Earth as if it were falling through air. Okay, because it is such a small volume and such a high mass, and therefore such a high density. Okay, that's the idea behind a neutron star. Okay, that's how dense a neutron star is, and that's how dense the nucleus of an atom is. It's crazy. Cool. Guys, there's your introduction to subatomic physics. It's beautiful. That is just the surface of an incredible world of subatomic physics that I hope, and I know that some of you will learn eventually as you go further in your studies. Okay. What is your homework for tonight? It's pretty easy. So let me explain your homework right now. Your homework is due at 8 o'clock, due by 8 o'clock tonight. Okay. Okay, so that's the first thing. It's due by 8 o'clock p.m. tonight. Number 2, it's due to my email, randyforsyth@gmail.com. Okay, now what does your email need to contain? First of all, your subject line needs to be Physics 11th, Class 86. Exactly. Okay, I'll put that in the homework. I'll put that in Google Classroom too, but make sure your subject line is exactly Physics 11th, Class 86. I do that for a reason, because I need to be able to search for your emails, and if you don't do the correct subject line, then I can never find your correct homework. Okay. Now, there's a subject line, Physics 11th, Class 86. Now, what does your email need to contain? Okay, it's pretty short. You need to choose one of these 9 topics we discussed today, just one, and explain it to me in your own words. Okay, just one. You could choose nucleons, or you could choose femtometer, or whatever. Any of these 9. Okay. Now, how long does your email need to be? I'm not going to put a specific sentence limit on it, but I want you to send me an email that is more or less like 4 sentences. Okay. Don't send me like a super long email, because I don't want to read a ton of novels today. I'm not going to minus points if you make your email like 5 or 6 or 7 sentences, but don't make it like super long, and don't make it like 2 sentences. Okay. Make it around like 4 sentences, explaining to me in your own words one of these topics. Now, let me be really clear. If your subject line is different than that, if you have like a lowercase c, or if you don't have a space between class and 86, or if you have lowercase p, if it's not exactly that, spaces, lowercase, uppercases, then that's a 0. Okay, because I need your subject line to be exactly that. Cool. Everything's clear, guys. I love you. I'll miss you. Although this is not our last class, because we will do the exam review on Thursday. So anyway, guys, thank you for all of your hard work, all these years. It has been an honor to teach you. And it's crazy that this is the last class I get to teach you. Makes me sad, but I'm also really excited for you guys and what you have coming. Whatever career you choose, there's a lot to look forward to and a lot to be excited about. So I'm very excited to see what careers you choose and what your life looks like. Your career is only part of your life. There's so much more to life than your career. But I hope that you guys enjoy university, and I'm very excited to watch you from a distance and see where life takes you. So love you lots. I will see you guys on Thursday for our next class. And yes, I don't know how to end this last, what do I say for the last time I ever teach you a lesson? Like what's the last words I say? Okay, here's my last words. I love you lots, and I'll miss you. Bye bye.